Hello, everybody, and welcome to your lecture 16 for Historical Geology. I'm Dr. Hurt. We're going to be going over Archean Geology. So we're continuing our march right through time. Still, we've moved out of the Hadean, and we're going on to the next eon, the Archean. So we're going to learn a little bit about what happened geologically during the Archean. So gird your loins and get ready. Here come the rocks. So we're going to go over first just a little bit of review. I got my lecture assignment packet with me. I hope you have yours too. So the Archean is a what of geologic time? It's an eon, right? So it's one of the four big categories of time in geologic history. We have four eons, right? The Hadean is the first, the Archean, the Proterozoic, and of course the Phanerozoic. Welcome to the Phanerozoic. It's the Phanerozoic right now. So anyway, we are going on to the second eon. That is the Archean. Okay, so we can go on with this little thing. Whoops, we went too far. So there's a artist's conception, of course, of the Archean. I want to point out a few things to you that are kind of interesting. So if you remember when we looked at the artist's conception of the Hadean, it was, I don't know what you can say, a hellscape. It's called Hades, right? Hadean for a reason. It's hellish, right? It's full of volcanoes and magma, lava spewing out, and clouds of sulfurous gases and all this nasty stuff. But if you look at this picture, it's starting to look kind of nice, right? So you see volcanoes, a lot of volcanoes. We're going to talk about that. You can see still, we like to show the moon being very close. Remember, and I talked a little bit about that in the last one, the Hadean. I'm trying to get my pen to work here, but it always gets a little bit weird. There we go. Let's see. No, still doesn't work. That's very annoying. Don't know why it's not working. Sorry. Pen. There we go. Okay. So we see the moon here. Okay. So one of the big things is the moon is still very close to the Earth. You know, the moon's been moving a few centimeters away every year, and it's so it used to be a lot closer in the Archean. We see still a lot of volcanism. Okay, but notice we also see water for the first time. Earth has cooled down enough to let water start to form on the surface. We still see intermittent not comet, I should say, but meteorite and asteroid strikes. So there's still a lot of accretion going on. But things are looking very different, right? Cooler. And also, what's all this stuff? What's all this? These little bumps. You can see it in the last picture, too. There's lots of little bumps. These bumps. Okay, so all those bumps are stromatolites. We're going to talk about those. Whoops, I dropped my pen. They're stromatolites, and we're going to talk about those in the next lecture. Okay, so some of the earliest forms of life on Earth. Okay. So yes, the Archean is a eon, and it went from the end of the Hadean, ending 4 billion years ago, to the start of the Proterozoic, 2.5 billion years ago. Okay, so you have, what's that? 2.5 billion years of history there. Okay, so it's a very long, or actually, no, I'm sorry, 1.5 billion years of history. So the geologic time is divided into how many eons? 4 eons. Every eon is subdivided then into, you know that every eon, right, is subdivided into its own eras. You do not need to know the eras of the Archean. I don't ask about it on the test or anything like that. I don't even present it here. You'll notice that the eras is conspicuously missing for the Archean right there, okay? So you got all this stuff up to number 4, I think, and the Archean extends from 4 billion years ago, 4 GA, to 2.5 GA, okay, with the start of the Proterozoic. All right, so we're going to talk about the second eon, the Archean. Here's another depiction of geologic time that I like as a pie chart, and you can see that we've gotten done with the Hadean here, and the Archean's pretty big, okay? It's a pretty big chunk of the time. It's kind of crazy because the Phanerozoic that we're in right here, that's the Phanerozoic, but it is dwarfed by the size of the Proterozoic and the Archean. So the Archean and the Proterozoic lasted a long time. In fact, together, the Proterozoic and Archean is the vast majority of Earth's history. Okay, so the Archean covers about 33% of Earth's history. Together with the Proterozoic, that's 75% of Earth's history in these two Little eons. They're not little eons, they're big eons. But it's amazing because what was life like here? It was all pond scum. Okay, so pond scum, pond scum, pond scum, all the way up for that's vast majority of Earth's life on Earth was just pond scum, right? You didn't really have advanced animals till the end of the very end of the Proterozoic. Okay, so we are covering. It's kind of amazing if you think about it. We are covering 75% of Earth's history in only 2 lectures. Doesn't seem to make any sense. But the reason that we do that is because it was a long time ago, and we just don't know very much about what happened in the Archean. There might have been a lot of things that happened, but we don't know about it because the evidence is gone. There's no historical records, and there's not very much in the rock records, not very much in the fossil records, so we don't have very much to say. So that's why we're covering this vast swath of time in just 2 lectures. Whereas once we get to the Phanerozoic, we're going to have I think 2 lectures on Paleozoic, 2 lectures on Mesozoic, 3 lectures on Cenozoic. Right? So it got a lot more information because it's much more recent. That's why. All right. So anyway, the Hadean ended with some of the oldest rocks on Earth. The Acosta gneiss marks the end of the Hadean, with the oldest rocks that we have, 4 billion years old. And we start the Archean. So why don't we have any Hadean rocks? Or we don't have any Hadean rocks. We do have Archean rocks. Okay, it's because the Hadean, really, that's kind of what marks the end of the Hadean, is the first kind of oldest rocks that we have. Okay. All right, so the Archean went from about 3.8 to 2.5 billion years, about 4 billion years, 2.5 billion years ago. The word Archean comes from ancient, the Greek word for ancient, archaic, okay? And it marks the birth of the first continents and of life, okay? So it's really important things that happened in the Archean. When you think of the Archean, what I want you to think about is continents, and some of the first life, okay? A little bit of new vocab for you. So, like I said, we're going to be talking about continents, a lot about continents and the birth of continents. And a lot of times when we talk about continents, kind of the anatomy of a continent, just to kind of give you some understanding here, okay, some vocab here. When you have a continent, you kind of have the crystalline basement rocks, okay, we call them the basement rocks. What does that mean? Well, that's the stuff that's like igneous and metamorphic rocks, okay? And you might remember sedimentary rocks are kind of like the thin skin that's on top. So hopefully you remember that from the sedimentary rocks and sedimentology lectures, that you have sedimentary rocks are actually not very much of the total volume of the crust, but they're a lot of the surface area. So you have these basement rocks, which consist of like the crystalline, granite, plutonic, diorite, or metamorphic rocks, okay? And then you have the thin skin of sedimentary rocks on top. So the cores, the oldest like interior of the continents, we call those the cratons. They're the cratons, okay? So the cratons are like the old interior cores, often archaic in age, Archean in age, sorry. And now cratons are they're subdivided into the shields and the platforms. So shields are cratonic rocks that are exposed at the surface, whereas platforms are cratonic basement rocks that are buried beneath more recent sedimentary rocks. Okay, so in a place like Corpus Christi, we're on something more like a platform. Okay, so if that, because we're coastal, I don't know if I really even want to say we're really like the basement rocks are really deep basement granitic rocks that are here, or dioritic rocks, probably from the Phanerozoic, not from the Archean or older, or younger. But anyway, platform is craton covered with sedimentary rocks. Shield is where it is exposed. You actually have the oldest rocks exposed. A lot of times in North America that happens in like Greenland and Canada. We don't have too many parts of the country. Maybe in Montana, Wyoming, you can actually look at real shield, okay, North American shield, okay. So that's number 7. What's the difference between cratonic? craton shield and platform. It's just a matter of being covered with more recent sedimentary rocks or not. Okay, now what is the continental crust made out of, right? Now you might remember that it says true or false. Composition of continental crust is mostly basaltic. That's a big fat false, right? You might remember that the ocean crust is made out of that beautiful. It's not beautiful. It's actually really boring and ugly. The basaltic rock. Okay, so there's your basalt. It's black, dark-colored rock, pretty plain, not much to look at. Whereas continental crust is mostly made not of granite. Don't listen to Miss Frizzle if she tells you it's made of granite. It's not. And actually, a lot of textbooks will even say that the continental crust is made of granite. But actually, it's mostly a rock called diorite. Looks like that. It's kind of salt and pepper colored. It's intermediate in its composition. That means it has an intermediate level of silica, unlike granite, which is high in silica, about 77-75% silica. This is more about 60%, 65% silica. That's the average for continental crust. But it's made of that beautiful rock, diorite, mostly, okay? But of course, continental crust is very heterogeneous, so there's a lot of different stars. Is there basalt in continental crust? Sure. But mostly, on average, it's mostly diorite, okay? So anyway, here's a map showing distribution of Precambrian rocks. Precambrian means before the Phanerozoic, before the first period of the Phanerozoics, the Cambrian. So these are Precambrian rocks. You can see that a lot of the continents have the red shows you Precambrian shield. Okay, the green is showing you platform. So there's Precambrian rocks there in the green areas, but they're underneath sedimentary rocks. Okay. So there you see in the purplish color, that kind of beigeish, ugly purplish color, the oldest centers of the continent. So you can see for North America, it's mostly up here in Canada and in Greenland. That's where you're going to find exposures of the Archean crust. Okay, the really cool old stuff from the Archean. Okay, there it is right there. Greenland and in Canada. Okay, so the beige color, on the other hand, represents continental crust that would have been present in the Proterozoic, okay, but maybe not in the Archean. So you have Proterozoic cratons there. Okay, so remember, Proterozoic would be Precambrian as well. Okay, remember, Cambrian, Precambrian refers to anything before the Phanerozoic. So it's basically the three previous eons. All right, so this is a really important graph. I'm also looking at number 9. It says, if we look at the modern seafloor, what percent of the rocks on the seafloor are Archean in age? Well, you'll notice that the seafloor isn't even color-coded in this picture, right? And the reason is number 9, and by the way, I'm sorry if the numbering is off. Hopefully the numbering is correct. But suffice to say, if we look at the modern seafloor, what percent of the rocks of the seafloor are Archean in age? It's a trick question. The answer is 0. Remember that the seafloor made of that beautiful basalt right there, okay? The seafloor is never older than 180 million years old. Or maybe, I guess there's actually part of the Caspian Sea that's a little bit older. But it's none of it is Precambrian. None of it. So that's a trick question, 0. Okay, the continents is where you get preservation of really old continental crust. Okay, or crust, I should say. Ocean floor constantly gets recycled. Right, there's our little lava lamp right there. It's not hot enough to start moving, but it's convecting, right? And you know that just like the lava lamp, the old cold ocean crust is going to sink down to the bottom, to the core mantle boundary. The hot, buoyant material is going to rise and come up at mid-ocean ridges. But suffice to say, ocean crust keeps on getting recycled. So if you look at the modern seafloor, none of that seafloor is Archean in age. So that's a trick question. Okay, so anyway, here is your beautiful graph showing the amount of continental crust, percent of the continent, current area of the continental crust, and how old it is. Okay, so you can see that if we look at the percent of the current area, you can see that it was starting to be actively built starting in the Archean. Okay, so the Archean is when continental formation really kicked into high gear. We get the birth of the continents. Okay, by the time you get to the Proterozoic, most of the continents have basically already been built. So most of the continents have already been built. So the Archean, again, when you think Archean, you should think continents. This is when the continents came into being. Okay, so by the end of the Archean, continents were 80% of the current size. Okay, that's why the average age of the continents is, over 2.5 billion years old. Way older than the average seafloor. Average seafloor is maybe only at most 100 million years old. Maybe even less, 70 million years old. Average continental crust age is about 2.5 billion or so. So that's because most of the continent was created in the Archean. Okay, by the end of the Proterozoic, the continents were basically the same size as they are now. So continental crust is still forming, but nowhere near like it used to be in the Archean. That's why we keep showing in this video here, or not this video, I'm sorry, but in this picture, you see big volcanoes, big continental crust forming volcanoes. These are subduction zone volcanoes. Remember that continental crust, right? There's your continental crust. Continental crust is created at subduction zones, okay? So that's why, again, in this picture, you get these big subduction zone style volcanoes creating continental crust. Okay, so going back to your lecture assignment, it asks you, what kind of tectonic setting is continental crust formed at? It's formed at subduction zones. Okay, it's formed at subduction zones. Now, I hope that you remember from the plate tectonics lecture, you need water to make continental crust like that. If you don't have water, you can't make continents. You can't make continental crust. If you go to Mars, maybe you'll go to Mars someday. Who knows what's going to happen in the future? Maybe people will be able to space travel to Mars on vacation. But if you go to Mars, you won't find any continental crust. It's all boring black basalt. Ocean crust, basically. We don't have any of the continental crust on Mars or Mercury or Venus. Okay, it's only an Earth thing. Continental crust is a total Earth thing because we have water, and you need water to make continental crust. So you get continental crust made only at subduction zones, and you need water to make it because water lowers the melting point of the mantle and allows the mantle to melt, partially melt, and form andesite and intermediate volcanisms, diorite, things like that. Okay, so remember that at a subduction zone, you might remember how this goes from the plate tectonics lecture. You have all that water seeped into the ocean crust. Okay, it's like a sponge. Okay, rocks are like a sponge. They soak up the water. So the water seeps into the ocean crust. It gets subducted, and that water gets pushed out into the mantle. And in the mantle, that water lowers. Okay, I'm going to write this because it always gets confused. Lowers the melting temperature of the mantle. So it's just like throwing salt on ice. When you throw salt on ice, what happens? It melts, right? Why does it melt? It melts because the salt lowered the melting temperature of the ice. Okay. So anyway, when you throw water into the mantle, it lowers the melting temperature of the mantle. It causes the mantle to melt, and you produce arc volcanism. Okay, arc volcanism. You produce these volcanoes that create diorite, andesite, things like that. Okay, so when ocean crust is subducted into the mantle, does it contain water? Yeah. What happens to the water when the plate subducts? It gets pushed out. The high pressure and high temperature drives the water out of the plate. What effect does that have on the hot mantle rocks? It lowers, right there, you got it on the screen, lowers the melting temperature of the mantle. And what does that produce? That produces, by partial melting, that flux melting, you lower the melting temperature of the mantle, it's flux melting, and it produces basalt. Okay, produces basalt. So I'm turning the page, next page, okay? Now what does partial melting mean? Partial melting means that the mantle doesn't 100% melt. It only partially melts. It only partly melts. Okay, so usually when flux melting occurs, only about 30% of the mantle actually melts. It produces basalt. Okay, so I'm going to draw this for you. Okay, you ready? It produces basalt. Whoops, I'm trying to get some, like a nice red color for the lava. Okay, there we go. And the basalt gets emplaced into the bottom of the crust, and it builds up and it builds up and it builds up until the basalt partially melts. And when the basalt partially melts, then you start to erupt andesite and diorite, and that's what creates the continental crust. Okay, it's the partial melting of basalt, which came from the partial melting of the mantle. Okay, clear as mud? I hope so. No, I hope it's really clear, but if it's clear as mud, that's okay. You don't have to have a perfect understanding of this for the test, but you do need to be able to at least get it in the first go-around, put on your lecture assignment. Okay. So what kind of magma or lava is produced when basalt is partially melted? It produces that intermediate style diorite or andesite. Okay. The intermediate. Remember that basalt's mafic. What is the composition of the continental crust on average? The continental crust. It's diorite, right? Intermediate, just like what is produced at subduction zones. What kind of lava is erupted at volcanic arcs at subduction zones? Diorite, andesite, okay? Intermediate. So the answer in number 16, 17, 18, it's all the same. Intermediate, 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 intermediate. It's diorite / andesite. Remember, andesite is the volcanic form of diorite. Diorite is the plutonic form, okay? So it's intermediate, intermediate, intermediate. The important thing you need to understand here is that subduction zones is the birthplace of continental crust. They're such special places, and there's a lot of questions about it on the test because they're such special places, okay? It's where the ocean crust goes to die. So the ocean crust dies. The continental crust is born. From the ashes of the ocean crust arises the continental crust. Okay? So that's how it all works. It's an extremely important place. I'll move on because I don't want to go on and on and on and on and on. Okay? But hold off on number, asking you to draw a picture of a volcanic arc. Just hold off on that. We're going to get to that just a bit. Okay? Okay, so we're going to kind of skip that one about drawing. Looking for my coffee. I need to have my coffee. Okay, I'm going to skip that one, just kind of drawing a volcanic arc because I want to wait till we talk a little bit about back arc basins. Okay, so let's go on. Most of the Archean rocks that we find, what kind of rocks are they? Most of them are granite gneiss complexes. So they're plutonic rocks with maybe some gneiss, which is a metamorphic rock, thrown in there. Okay, so there you go. There's some typical Archean rocks. Those are gneiss, some gneiss. And you can see the banding in this. That's the gneiss. That's the metamorphic rock. This, you can see it gets cut off, and there's actually some granite. There's like a granite dike cutting it off. That's the granite. Okay, so it's a plutonic rock. plutonic igneous rock, and this stuff's metamorphic. Okay. All right, so that's pretty common. Pink Archean granite cut by Proterozoic basaltic dikes there in Laramie Range, Wyoming. Okay, so there's some Archean rocks. It's a place where you can go. You can go to Wyoming, like I said, or Montana. See some real Archean rocks in America. Otherwise, you got to go to Canada or Greenland. Maybe that sounds exciting to you. I don't know. Archean gneiss. There's some beautiful Archean gneiss in Scotland. Okay, it's another place you can see some of the shield, right? Cratonic shield. Okay. Now the other 10%, so 90% is granite gneiss complexes. 10% is this stuff called greenstone. Greenstone. And there's a picture of greenstone looking a little bit tinged bluish green, right? Hopefully you can see that. Like I said, it's only 10%, so there's not much of this stuff around the world. There's some areas where you can see Archean aged greenstone, okay? So Archean aged greenstone. So greenstone belts consist of metamorphosed volcanic rocks mixed with marine sedimentary rocks. Okay, so that's intermixed: volcanic, sedimentary, marine sedimentary, volcanic, marine sedimentary, volcanic, marine sedimentary, all on top of each other, metamorphosed. That green color that we see, that green color is from two minerals, chlorite and actinolite. Actinolite's kind of amphibole. Okay, so chlorite and actinolite. All right. So greenstones are sequences of Archean marine sedimentary rocks, like I said, and mafic basaltic volcanic units. Okay, and they're usually kind of folded, like I show right here. You can see that these are usually very old, so they've been through the ringer, right? So they're usually pretty old and contorted, and they've been squeezed, they've been faulted, they've been folded. They're pretty nasty. Here's some granite, Archean age granite intruded into those greenstone belts. Trying to show you greenstone belts. They're often in these kind of synclinal. Synclinal means these folded bowl-shaped fold. Do you see the bowl-shape depression fold? Okay, like that. Okay, so they're often in those kinds of folded units, often intruded by granite. They often form call them belts, because they often form like these mountain belts. Here's some in South Africa, right? So how do we think these things form? Okay, how do we think they form? And this is kind of more what you want to draw for the previous question. It says below, please draw a picture of a volcanic arc. Okay, so this is a little bit more what you want to draw, something like this here, okay? Because I want you to form to show the back arc basin as well. So you have the ocean crust subducting. You have, or something like this, right? This would work too, this top picture, either one. You have this ocean crust subducting. There's flux melting going on here. What causes the flux melting? It's the water entering into the mantle and lowering the mantle melting temperature. I'm sorry, not the mantle temperature, but the melting temperature creates the basaltic magmatism, partial melting. That creates in turn partial melting of basalt, which erupts the andesite and diorite here. Okay, so then you form continental crust in the form of volcanic arc. Okay. Now the back arc basin is this area behind the arc right here. And there might be subduction going on the other side too, like this, okay? It's a really important process. You have these two subduction zones that collide with each other and accrete together the continental crust. And that's slowly how accretion of continental crust occurs over time, okay? So anyway, the back arc basin consists of volcanic rocks, mafic volcanic rocks, like basaltic volcanic rocks, mixed with marine sedimentary rocks, because you can see it's underwater here, okay? A very good example of a back arc basin right now is something like the Sea of Japan. That's right. So Japan, the island of Japan, is a volcanic arc. Okay, this would be the back arc basin right in here. Okay, so it's building up volcanic rocks along with marine sedimentary rocks. Okay, so we think that greenstone belts formed in areas like that. So you get subduction begins, you get flux melting, producing a basaltic liquid, you get new continental crust. Okay, that's the volcanic arc. As that volcanic edifice erodes, you get marine sedimentary rocks with a lot of mafic, and intermediate volcanic pebbles and sand, right? That makes a marine sedimentary rock. And then eventually that collides in a new subduction zone, and it creates that synclinal bowl shape, right, as subduction continues. And that's how we get these beautiful greenstone belts. Okay, so that's what we think. All right, so notice that in these artist conceptions, the Archean, there are always oceans. So why do we think there were oceans? Okay, there's a lot of evidence for oceans in the Archean. So many things. Okay, what's one thing? Actually, right here you see all the answers to the questions in your lecture assignment, right? We see that there are subduction zones. You need water to get continental crust in these subduction zones, right? We've talked about this a lot. You need to have water to power the flux melting that creates the continental crust at a volcanic arc. Just the fact there's continental crust says, hey, water, okay? So there's water. You know that just from the presence of continental crust, okay? What else do you see here? You see that there's life. Okay, you see the stromatolites. We talk about this in other lectures, right? The first origins of life, stromatolites. So stromatolites obviously need water. Okay, so we actually think that at the beginning of the Archean, Earth was totally covered with water. It was water world. It was all water. Because you need to have the oceans to make the continents. So before the continents could even exist, there had to be ocean. Okay, so it was probably covered completely with water at that time. Another line of evidence is we have these rocks from the Archean. These are 3.8 billion year old pillow basalts. Pillow basalts only form underwater. The only way to make pillow basalts is to form them underwater. This is a video showing the basalt actively forming pillow basalts underwater. Okay, so it's an underwater rock. So it's pretty cool. I don't know how much of it you want to watch though. All right, so what evidence do we have that plate tectonics was happening in the Archean? So much, right? We have the presence of continents. You need subduction zones to make a continent. You can't make a continent without subduction zones. You can't have subduction zones without plate tectonics. So there we go. We know that plate tectonics was almost certainly going on at that time. Present, greenstone belts we think were made in these volcanic arc subduction zone environments, back arc basins, right? So we have a lot of evidence for plate tectonics going on in the Archean. Okay, so don't just say, explain your evidence there. Don't say, oh yeah, there was plate tectonics. Explain why. Well, we have continents. We need to have subduction zones to have continents. We have back arc basin greenstone belts show there were back arc basins forming in subduction zones. So we know that there must have been at least subduction zones and therefore plate tectonics. And probably mid-ocean ridges too. But are we going to have any mid-ocean ridge rocks left over from the Archean? No. Right? We're not going to have any of that left over from the Archean because all that stuff gets subducted and it gets destroyed. That's why we don't have any Archean ocean crustal rocks. Okay. So anyway, next time we're going to be talking about life in the Archean, the origins of life. Get ready for stromatolites. We're going to talk a lot about stromatolites, the first evidence of real clear evidence of life on Earth. So I hope you enjoyed the lecture, and I will catch you next time. We'll talk about origins of life. So thank you for tuning in.